Okay, yeah. Thanks everyone for coming to Michael's Alcorn's PhD defense today. Michael joined Auburn at my lab to do a PhD 3 years ago, and it has been a real pleasure to work with Michael. And he has been example to former students in the lab and also current students in the lab. There are a lot of ways, from excellent communications to strong work ethics. I remember the first semester he woke up at 2 a.m. just to run some jobs in order for us to catch up the deadline in November. He joined in August. It has been normal, that work ethics from Michael. He also is a to-go place when people have bugs or questions with their own projects. They always go to Michael and ask. So yeah, and I hope you will enjoy his defense today.
Thank you. Okay. I'm assuming everyone in the chat can hear me, or in the call, based on the reaction so far. Yeah, can you let me know, Captain, if anyone has issues? Okay. All right. So yeah, thank you, Anh, for that introduction. And thank you everyone for being here today. Before I get started, I want to again thank Anh also specifically for giving me the chance to do research in machine learning, which is something I think I would have always felt was missing from my life if I hadn't been given the opportunity. So I'm very grateful for that. I also want to thank my committee, Jan, Hans, Levent, and I want to thank my university reader, Rob, and also our Director of Graduate Programs, Professor Chen, all of who played an important role in making today a reality. And so you'll notice on these slides that there are links. The slides for this talk are available on my website. So if you want to find out where those links go, they're going to be throughout the presentation. You can find them on my website. All right, and so for those who don't know me, I thought it'd be fun to give a little bit of a background about myself, because I took kind of a weird trajectory to get here. And so to make a long story short, I graduated with a bachelor's in zoology from Auburn in 2010, then enrolled in a PhD program in evolutionary biology, which I promptly dropped out of. And then I started to teach myself the program, eventually made my way through a master's program and worked a little bit in industry before re-enrolling in the PhD program here at Auburn, facing many rejections along the way. So it wasn't necessarily the most efficient route, but hey, I made it. And so today I'm just going to be talking about several chapters from my dissertation. There's not really a strong unifying theme through the work, but I think one of the really cool things about machine learning for me is that if you know some math and how to program, you can work on a bunch of different really cool problems. I'm also not going to be discussing other projects that I've worked on as a student at Auburn, including one of the chapters from my dissertation that extends the first chapter I'm going to be going over. I was also a co-author on a project led by my lab mate, Chi. He has a nice presentation of that available online if you want to find out more information about that. I also won't be discussing R&D work I did with Adobe Research and the Cleveland Indians as an intern because those results aren't public. And so the slides for each of these chapters are going to be abridged versions of longer talks I've given. And so if you want to find the full slide deck, you can click on the link in the title slide for each chapter. And so this first project was accepted to the 2019 Conference on Computer Vision and Pattern Recognition. So hopefully I don't have to explain to everyone here that artificial neural networks are really great. They're being used for things from self-driving cars to facial recognition and even in medical applications. But they're still far from perfect, as you can see, as demonstrated in these headlines highlighting specific AI failures. So by systematically studying these failures, we can help researchers develop more robust algorithms. So on this slide in particular, what we're looking at is an example of adversarial machine learning, where on the left-hand side, we have images of objects that the neural network has correctly classified. In the middle column, we have what looks like noise, but is actually very precise noise that when combined with the images on the left, causes the neural network to make a specific misclassification of ostrich, even though to the human eye, they all look similar, like the actual object that it should be classified as. In this project, we set out to use 3D graphics to discover natural failures. And so what I mean by that is that in contrast with the previous type of adversarial example where we were manipulating the digital pixels, we want to be able to find examples of scenes in the world that will, without manipulation, would cause a neural network to make an error. To give you an example of what I mean by that, so on the left-hand side here, we have a 3D school bus overlaid on a natural background. And what you can see is that the neural network made a correct classification with a high probability. In the middle, we then rotated that 3D school bus onto its side. And you can see that the neural network made an incorrect classification. And on the right-hand side here, we have the actual image, which features a school bus that's been in an accident. And you can see that the neural network is making the same misclassification. So the motivation here is, can we use 3D graphics to find these types of failures that might occur in the wild? To do that, we collected a data set of 30 3D objects that you might find in the traffic environment. And then we randomly sampled 1 million poses for each object and recorded the classification and the probability of the classification. Surprisingly, we found that neural networks are confused by 97% of the pose space. And so what you see here in this figure is the distribution of different pose parameters that were correctly classified by the neural network. And what you can see, for example, like on the Z delta figure, is that the neural network seems to be highly biased towards images that feature the object close to the camera. And so this might be what we expect because most of these data sets are curated. And so the labels that are being assigned to are the object that's going to be in focus and sort of close to the camera. Additionally, you can see that, for example, the neural network really doesn't like it when you pitch an object 90 degrees in either direction. Again, that's probably a reflection of what we typically see in these types of curated data sets. In addition, we found that neural networks are highly sensitive to pose perturbations. So what I mean by that is you can start from a correctly classified image and minutely change the pose of that object, and it'll cause the neural network to make a misclassification. And so we can see in this case is that in that middle image, we have a correctly classified school bus. And just by rotating the school bus a little bit on the roll, we quickly drive down the certainty of the model with regard to that specific classification. In addition, we found that we could use black box optimization to discover specific failures. And so what I mean by that is we could say we want the neural network to make a specific misclassification, in the case of this GIF, a power drill, and then optimize the pose parameters to discover an image with the object in that particular pose that would cause a specific misclassification that we wanted. So what you can see here is that the neural network eventually thinks that this school bus is power drill with a very high probability given that particular pose. Importantly, we found that these adversarial poses transfer to different neural networks. So basically, what that means is we can find an adversarial, a natural failure for one particular neural network, like this Inception V3. And then when we show it to a different neural network, like the ResNet 50, it also makes a misclassification. And so these failures are not specific to a specific architecture. In addition, I developed this open source GUI tool that allows users to sort of try and discover their own natural failures using the mouse. And so basically you can just manipulate in the scene, the object's pose, the lighting in the background, and see whether or not you can make the neural network fail in various ways. And all of the code for this project is available on GitHub in open source. So to summarize, neural networks misclassify 97% of the pose space. These neural networks are highly sensitive to, we found these neural networks are highly sensitive to pose perturbations, and these adversarial poses transfer between neural networks at a very high rate. So what we think these results suggest is that the standard neural network training pipeline can lead to incredibly naive models. So researchers might have to rethink how they approach these particular tasks. Okay, I'm going to shift gears considerably now into multi-agent spatiotemporal modeling. I gave an hour-long version of this talk for the Auburn Data Science, Statistics and Data Science seminar series, where I go into like the nitty-gritty details. And so if you're interested in like, if you find this talk, this particular chapter interesting, you can check that out. And this chapter and the following chapter are still both under review, but they were actually recently cited in a DeepMind paper, which was really exciting for me. Okay. So if there are any basketball fans in the audience, I want you to take a few seconds and try and predict what's going to happen shortly after this frame featuring LeBron James trailing behind a person going in for a layup. Let's see what happens. So most basketball fans probably could have told you what was going to happen there because they've seen LeBron James in similar situations many different times. And what often ends up happening is LeBron makes the block. So my goal with this particular project was to design an artificial intelligence that can learn to quote unquote understand multi-agent spatiotemporal systems like the game of basketball simply by watching them, much as humans can do. So in the long term, you could use these types of models for counterfactual analysis. So in the case of basketball, that could be to project the impact of trades or predict the outcomes of different plays. But there are certain challenges that come with modeling multi-agent spatiotemporal data. Specifically, agents are unordered and interact in complex ways, which leads to interesting design challenges when trying to come up with your AI algorithm. Additionally, sequential data is large and cumbersome to work with, and so we need to keep computational efficiency in mind when coming up with our particular model. I want you to keep the two tasks I want you to keep in mind that I'm going to be trying to model here are modeling the trajectories of the players, so where the players are going on the court, and then also modeling the trajectory of the ball, given everything that's on the court, including the players. So before I get into my architecture, I want to talk about what makes multi-agent spatiotemporal data so strange. And so to do that, I want you to consider a simplified trajectory prediction task where you're given the locations of the players on the court at one time step, and you want to predict where they will be just one time step in the future. So we only have one frame of input, and we're only trying to predict one frame of output. How might you approach doing that? And so one naive strategy would be to use what I'll refer to as a bag of players representation, where each player in the entire NBA has his own slot where his features go in the input. And so like what you can see down here on the bottom is anytime Steph Curry is involved in the play, his coordinates on the court and whatever other information you want to include about him go in these slots. And then anytime LeBron James is involved in the play, his features go in these slots. The issue with this particular approach is that it's not data efficient at all because the vast majority of the players in the NBA are not going to be involved in any particular play because there's only over 10 players on the court. So that makes it really wasteful in terms of each of your sampling efficiency and in terms of the number of parameters that the model requires. Additionally, each lineup is basically a completely different input with this particular representation, which makes it unclear or hard to predict how the model will generalize to different lineups, for example, following a trade. And there's also no way of handling new players. And so you can imagine that you have this way of mapping a draft pick, so like a new player coming into the league to a particular feature representation. You can't just plug that into this model. You have to basically extend the input where that player's features can then go and then sort of retrain the model from scratch. Naive strategy number two would be to use a vector that is only the number of players on the court long, so 10 in this case. The problem with that is that where do you put the features for each player? You can't just use the position, not their nominal position, because players often play multiple positions depending on the lineup. And so for example, LeBron James can play any position on the court given the particular situation and where his team needs him. And so it's not, you can't just assign him to a single slot every single time because that doesn't really translate to what other players are going to be doing. So the data structure I decided to work with, the way I decided to try to define what happens on the court is that as a sequence of sets. And so what I mean by that is that each time step, I combine the player's identity and location into a single player input, which represented by this circle, and place the inputs for all of the players on the court into an unordered set to capture the fact that there's no ordering as I indicated on no natural ordering as I indicated on the last slide. When you then arrange these sets for multiple time steps in a row or in order, you get a sequence of sets. And so that's what we got down here at the bottom. And so again, the two tasks I'm going to be trying to model here are the player trajectories, where at each time step, each player has his own label indicating his trajectory for that time step. And then the other case is modeling the ball trajectory, where each time step only has a single label indicating the trajectory of the ball, given the players in the court and also the ball's position. And so given the sequential nature of this problem, I wanted to be able to take advantage of transformers, which are a new class of neural networks specifically designed for modeling sequences. And these models are incredibly powerful, as you can see in this recent headline from the New York Times singing their praises. The way these transformers work is they process sequences in parallel using what's known as the attention mechanism. And one kind of cool thing about the attention mechanism is it kind of gives you a way to peer inside at what the model is thinking. And so what you can see in this figure here is the attention outputs for a model that was trained to do translation from English to French. And you can see which words in the sentence it's paying attention to when it's trying to translate each step. And so the standard transformer was designed for natural language processing tasks, which means that each time step, you only have a single input. And the way it models the dependencies between words is by using a self-attention mask matrix, where at each cell indicates whether or not the model can look at the word indicated by the row when processing the word indicated by, or look at the model indicated by the column when predicting the model, predicting the word for the model. It can look at the word indicated by the column when processing the word indicated by the row. That's what I wanted to get to. And so, for example, if we look at the second row here, when the model is processing this second word, it can look at both the second word and the first word when trying to predict the third word. All right, got through that. Okay, and so to generalize this transformer to multiple inputs at each time step, we rethought of this attention mask matrix as a reshaped attention mask tensor, a 4D attention mask tensor, where each cell indicates whether or not the model can look at a specific agent at a specific time step when processing another specific agent at a specific time step. And so by reshaping this tensor into a matrix, it lets us use the PyTorch transformer implementation out of the box without any additional work, which is nice. And so the input to this transformer, just to give you some concrete ideas here, is Tk by F, where T is the number of time steps, K is the number of entities or the agents. And so in the case of basketball, it's going to be 10. And then F is the dimension of the features that we're using for each of those players. So another challenge with this particular task is that the trajectories for players can be thought of as inherently multimodal. And so what I mean by that is you can imagine that you have a point guard who's at the top of the key, and there's a defender right in front of him. 50% of the time he might go to the left, 50% of the time he might go to the right. If we were to train this model using just a standard regression framework, the model would just predict that he would go straight ahead, which never actually happens in the data set. And so to capture the multimodal nature of this problem, we decided to treat it sort of as a classification problem where we bin the trajectories at each time step and then use the bin that the player ended up in at the time step as his trajectory bin label. And so what you can see on the right-hand side here is the distribution of trajectory bins that occurred in the training set. And then we just trained this model again as a straight up classification problem. So the training procedure for this model consisted of, we used 569 games from the 2015 to 2016 season, and then there were also 32 testing games. The procedure consisted of first randomly sampling a game from the season, then randomly sampling a starting time from the game timeline, and then using the following 4 seconds downsampled to 5 hertz as the input. We would then randomly rotate the court with a probability of 0.5 to account for the fact that whether or not a team is going from the left to the right or from the right to the left is completely arbitrary. And then we would then train on that sample. So this training procedure gave us access to about 82 million different training sequences, albeit overlapping, which is about 800 times prior work. As a result, we were able to train a much larger model than prior work. Specifically, our architecture was very close to the original transformer and had about 19 million parameters, which is about 70 times more than prior work. So does Order-Agnostic work? What we found is that it is an effective learning algorithm for multi-agent spatiotemporal modeling. And so one common way to measure the performance of a model in natural language processing is using the perplexity per word. And what the perplexity does intuitively is it gives you the amount of uncertainty in the model in a way that's equivalent to the amount of uncertainty in a fair die with the same number of sides. So if your perplexity was 6, that's equivalent to your model has the same amount of uncertainty as rolling a fair 6-sided die. And so what we found is that the perplexity trajectory for our model was much better than just using the train set distribution. Specifically, for the player trajectory forecasting task, the perplexity per trajectory was 1.64, which is better than a coin flip, and then 13.44 for the ball trajectory forecasting task. We also compared our model to a strong graph recurrent neural network baseline that had an approximately equivalent number of parameters. And what we found is Order-Agnostic is both 3.8 times faster than this model and also had 10.5% better performance as measured by the average negative log likelihood. In fact, even when we only gave our model half as much training time as the graph recurrent neural network, the model still outperformed, Order-Agnostic still outperformed the graph recurrent neural network by 9.1%. If we probe the model a little bit to see what it's doing, we can see that it's using information about all players on the court through time, in addition to player identity, to model these spatiotemporal dynamics. So, for example, I also train a model only using a single player, a randomly selected single player as the input for the entire sequence, and compare that to the full model with all 10 players. And what I found is using all 10 players improved the model's performance by 18%. So having the information about what everyone on the court is doing is really useful for the model. When I add player identity to the model, instead of just using a generic identity for all of the players, the performance improved a further 4.4% for the player trajectory forecasting task, and then 2.7% for the ball trajectory forecasting task. So interestingly, prior research either did not use player identity or found it didn't help. So we're the first to show that, which is what you'd intuitively expect. Also, I compared the performance of the model when evaluating on entire sequences of the test set versus just the first frame of the sequence. What I found is the model's performance when evaluating the entire sequence was 70.6% better, which just means that the model is using historical information when making those predictions of the later frames in the sequence, which is exactly what we want. Interestingly, the learned player embeddings, and so I was associating, the way I was encoding player identity here is by learning an embedding for each player. These learned player embeddings actually encode individual attributes. So what you can see here is a UMAP of the player embeddings, when you can kind of think of it as sort of like a nonlinear PCA, where you can clearly see that players are clustering both according to their position and their skill set as indicated by their shade. Another way to look at these player embeddings is by looking at nearest neighbors. And what we found is that the player embeddings seem to be capturing fine grain qualities of the players. And so, for example, one really amusing example is that the nearest neighbor for Pau Gasol, who's this 7'1" center from Spain, so he plays like a European style of basketball, is actually his younger brother, Marc Gasol, who's a 6'11" center, and also is from Spain and plays a European style of basketball. So I thought that was like pretty cool result. When we look at how the model's predictions change in different contexts, we can see that the trajectory distributions depend on both the historical and current context. And so we can see is that Order-Agnostic is less certain early in the sequence, which makes sense because it hasn't seen anything that's happened so far, so it has no idea where players are going. And it's also less certain when choosing what to do near a defender. So that kind of makes sense too, because at that point, there's a decision, right? And so we're getting into that multimodal aspect that we wanted to model. You can also, again, like I mentioned at the beginning, the cool thing about these attention mechanisms is that they kind of give you a way to peer inside what the model is thinking. And what we saw with Order-Agnostic is that different attention heads appear to be performing different basketball relevant functions. And so this particular attention head appears to be keeping an eye on the ball handler's teammates. And so each of these frames is from a different sequence, and the players are shaded according to the amount of attention the model is paying to them in that sequence or in that frame, where lighter shades refer to more attention. And so you can see that each of these frames, the model is really highlighting the squares, and those are the teammates of the ball handler. And so this particular attention head seemed to have learned that knowing who's on the same team is important, which is, obviously true for basketball. This particular attention head is really interesting because it seems to indicate when there's an open man. And so what you can see in this case is as the ball handler is moving in the key, there you see an open man at the 3-point line, and the model finds that before the pass is even made, and it anticipates the pass. And so again, the model learned these aspects of the game simply by being trained to predict the ball's trajectory. That's the only signal is given. So to summarize, Order-Agnostic generalizes the standard transformer architecture to sequences of sets by reimagining the attention mask matrix as an attention mask tensor. It's an effective and efficient algorithm for multi-agent spatiotemporal modeling that integrates information across agents and time, and it appears to understand the game of basketball as indicated by the fact that its embeddings encode these idiosyncratic qualities of players and the fact that its attention heads seem to learn basketball relevant functions. Okay, and so this next paper or this next chapter extends Order-Agnostic. And so there was an issue with Order-Agnostic that I didn't mention at the time, and that is actually common across multi-agent spatiotemporal models, which is that they implicitly treat agent trajectories as independent at each time step. And so you can see the graphical model here on the bottom left. This is basically what almost every multi-agent spatiotemporal model is doing implicitly with its loss functions, where you can see that the predicted or the trajectory for a player doesn't have any effect on the trajectory of the other player at that particular time step. And of course, this is a really strong assumption because agents are often under the influence of shared unobserved variables, which induce statistical dependencies between the agents. So for example, in basketball, a team is executing a play. So like if that's unobserved, which it is in our case, and is typically the case, then there's going to be statistical dependencies between the players where if you know where one player goes, that's going to tell you some information about where another player is going to go. So just a quick refresher, the joint probability of the trajectories can be written many equivalent ways using the train rule of probability. And all of these factorizations imply that there's much more complex statistical dependencies can exist between the trajectories. And so for this particular joint probability of these trajectories here, you can factorize them. Two factorizations are these two here using the chain rule, but they're completely equivalent in terms of the joint probability. And so instead of this graphical model on the left, we could actually use this graphical model on the right that captures these statistical dependencies reflected in the chain rule. So I just want to get out of the way, is it legal to condition on concurrent player trajectories? And so, yes, it is. You can basically think of this as revealing each player's future position after his trajectory has been predicted. So if we're going to try and do this in real time, and we were given the locations of the players on the court, we could just pick one player first to predict his trajectory and then use that predicted trajectory to then condition on that for the second player and so on and so forth. So this is completely legal. We don't need to look at the future to use this type of model. Okay. And I also want to highlight the fact that Order-Agnostic is a generative model. And so all this stuff I've been talking about so far completely applies. Specifically, by training Order-Agnostic as a classifier over trajectory bands, it's actually equivalent to treating the model as assuming that the trajectories for each player are generated from a mixture of uniform distributions with fixed bounds that partition the trajectory space. And so I actually worked through the math of how they're equivalent in my paper, if you're curious about that particular detail. And so how can we make Order-Agnostic learn these conditional dependencies? And so one naive solution is to adapt the Order-Agnostic attention mask such that it allows the model to look at player positions whose trajectories have already been generated, which is like I was just talking about before. So basically, we just extend the attention such that for like this player would be predicted first, and then we allow the second player, the model, to look at that player's predicted trajectory when processing that second player. The issue with this particular approach is that you can't use it with multi-layer transformers because doing so requires that you see the future. And so to just go through what that means here. So at this particular time step, you can see how all the attention connections are here. The yellow player can look at the blue player's location in the next time step. So it has that information. And so when we then at the next layer use the same attention connections, the blue player, when it looks at the yellow player, it is actually seeing information about itself from the future. And so this won't work. So Order-Agnostic solves this problem by using a specially designed self-attention mask to simultaneously process three different inputs. Sorry. Okay, and so to quickly summarize this figure, the circles and the diamonds are the same as Order-Agnostic, so just the trajectories and the player's location on the court. The additional piece here are these pentagons, which have both the player's current or don't have player's current. They have the player's future position and the player's trajectory for the current time step. And by making the attention mask only ever allow the model to look at previous items in the sequence, we're allowing the model to both condition on concurrent player trajectories without needing to look into the future. So we're able to capture that chain rule that we wanted to at the initial in the initial slides. And so again, the joint probability can be factorized in a factorial number of ways. So for 10 players on the court, that's equivalent to about 3.6 million different factorizations. And so, but again, they're all equal. And so during training, to encourage the model to learn we shuffled the order of the agents for each sequence to encourage the model to learn a joint probability of these trajectories that was permutation invariant with regard to the ordering of the agents. That means we can shuffle the order of the agents for a particular sequence, and the model will hopefully give the same joint probability no matter what order they're coming in. So does it work? As a toy experiment, we built a toy data set consisting of two agents who move completely in unison in a random direction at each time step. And so you can see that in this training sample here on the left. If we train a Order-Agnostic model on this data set, you can see that it doesn't learn to emulate the behavior of these agents at all, because again, it's making this an implicit assumption that the agent trajectories are independent at each time step. However, Order-Agnostic is able to learn to emulate this behavior really easily, as you can see on the right. We also tested Order-Agnostic on the same NBA dataset that I used for Order-Agnostic and used the same training procedure. So you can see here on the left, this is the ground truth of a particular example where we're trying to pay attention to what the red player here is doing. Order-Agnostic on this particular example, this is what it said the red player would do. And then on the right-hand side here, this is what Order-Agnostic said the model, or said the red player would do. And so you can see that Order-Agnostic is making the player do much more realistic behavior. I should say that this Order-Agnostic example is kind of cherry-picked. Lots of times it does like do the correct thing, but it's much more likely to make these sort of egregious failures than Order-Agnostic. To sort of quantify the differences here, we found that Order-Agnostic had 8.9% better performance than Order-Agnostic when modeling these player trajectories. And the performance benefits of Order-Agnostic were more pronounced at the beginning of the sequence, which kind of makes sense because that's before Order-Agnostic has had the opportunity to sort of infer these shared hidden variables that might be dictating the behavior of the player. So what I mean is, after observing a little bit of the sequence, Order-Agnostic might be able to like sort of guess the play, right? And so at that point, it's less necessary to, the statistical dependencies at that point are less necessary to know or to model. And so you can just see that gap here at the beginning, 16.1% is only 9.7% at the end. I also, to test whether or not the model was approximately permutation invariant with respect to the order of the agents, I basically I calculated the negative log likelihood for each test set sequence while randomly shuffling the order of the agents 10 times, and then took and calculated the percent error of each of those shuffled negative log likelihoods versus the original order. And so the average percent error for these shuffled sequences was only 1.5%. And you can see in this figure here, the unshuffled, so this is the x-axis is the unshuffled average negative log likelihood for the sequence. versus the shuffled average negative likelihood after shuffling it 10 times. And what you can see is that they're highly correlated with a correlation coefficient of 0.997. And so the model is approximately permutation invariant with respect to the order of the agents. Additionally, I found that Order-Agnostic makes better forecasts when conditioned on concurrent trajectory information from other agents. So sort of implicit in all of this was the idea that being able to observe the trajectory of another player would tell us some information about the trajectory of another player. And so to actually test whether or not that was true, I had calculated the performance for a particular player in a sequence when he was at the front of the order of the players. And then I moved him to the back of the order of the players and then randomly shuffled the other 9 players 10 times and compared the performance of the model for predicting the trajectory of the player when he's in the first position versus when he was in the last position for the shuffled 10 times. And what I found is on average, moving the agent from the first position to the last position improved his performance by 14.6%. And so seeing what the other 9 players was doing was really useful for how the model was able to predict the trajectory of a particular player, which is exactly what we would expect, given that we think they're coordinated. So to briefly summarize, Order-Agnostic applies a specially designed self-attention mask to a mixture of location and look-ahead trajectory sequences to learn the distributions of statistically dependent agent trajectories. Order-Agnostic can learn to emulate the behavior of perfectly coordinated agents, and it outperforms Order-Agnostic by a wide margin when modeling the trajectories of NBA players. And lastly, Order-Agnostic is approximately permutation invariant with respect to the order of the agents and demonstrably uses concurrent information from other agents to make better predictions. And so for the last chapter, I actually realized that Order-Agnostic's interleaved input design could be used to perform order-agnostic distribution estimation. And this was accepted to it's a long name, so I gotta look at the workshop on invertible neural networks, normalizing flows and explicit likelihood models at the International Conference on Machine Learning this year. Okay, so what is order-agnostic autoregressive distribution estimation? So that's a really jargon-full phrase. Let's try and parse that a little bit. So autoregressive refers to a specific type of model where the output at one step is used as the input at the next step. So the classic example of that in machine learning is a recurrent neural network that's being trained on sentences where the output word at one step is used as the input word the next step, which is then used to generate or predict the word at the following step. Distribution estimation just refers to trying to model the probability distribution of a particular data set. And again, I want you to recall the chain rule probability where the joint probability of a set of inputs, a particular multidimensional input, can be factorized in a number of different ways that are all equivalent. And so order-agnostic is to contrast it with fixed order. And so the previous slide where we were talking about a language model is a fixed order type of model because the sentences are always processed in the same order where the first word in the sentence is processed first, the second word in the sentence is processed second, and so on. With images, you can imagine, with images, a typical fixed order type of model is one that processes the images in raster order, where the pixels are processed from the top to the bottom and from the left to the right. With an order-agnostic model, we want to be able to assign a joint probability to an input regardless of the order that the features are coming in. And so like we want to be able to assign a joint probability to this image if the pixels are coming in this particular order, no matter what the order is. So why would we ever want to do this? I think that's a reasonable question to ask. And so if you want to be able to efficiently impute arbitrary missing values from an input, such as these examples on the left or on the right here. And so in this case, we have images where a square of pixels is missing from the center. And we have on the right-hand side here, rows of pixels that are missing, indicated by the red. If we want a single model that can impute those missing values using all of the available information, you have to do order-agnostic autoregressive distribution estimation. Alternatively, if you want to do preemptive anomaly detection in a system where input features can arrive asynchronously and in an arbitrary order, you again need OA. And so what I mean by preemptive anomaly detection is where you don't have to wait for all of the features to come in to say whether or not something is anomalous. And so you can imagine that we have these two different Internet of Things setups here on the bottom, where in one particular time frame, the features come in this order, and in another particular time frame, they come in this order because they can come in asynchronously. If we want to be able to detect whether something's anomalous as soon as possible for both of these cases, we need an order-agnostic autoregressive distribution estimating algorithm. Okay, but as you can imagine, order agnosticism adds considerable complexity to the distribution estimation task because again, the number of factorizations for joint probability is factorial. So as a result, most other models either assume a single fixed order for the input features or only use a small subset of the possible feature orderings in practice or are not autoregressive. So let's see if we can fix that. And so the architecture here is almost exactly the same as Molinari where in this case, the parallel sequences are one input is just a sequence of identities of the features. And so for the pixels, that would be like their row and column. Or for tabular data set, that would be the column of the input. And the other parallel sequence is identity value pairs. And so we have the identity, like the pixel, again, the row column, and then also the value of it. So for like the MNIST data set, it would just be a 0 or 1 indicate the pixel value. And so to test the efficacy of this model, which I refer to as the DEformer, which stands for Distribution Estimating Transformer. The first data set was to predict the pixels of the binarized MNIST data set, regardless of their order. And so these are some samples of binarized MNIST. And this is, again, like what they would look like if they're processed in one particular random order. In the other case, we were predicting the measurements of samples from this power data set. Again, regardless of their order. The power data set consists of over 2 million samples from a single household, which are in a tabular format, so like a spreadsheet. Where each sample consists of 6 real values. And for that particular data set, we were modeling it using a mixture of Gaussians, which has a likelihood that looks like this. And again, the code for all of this is online if you want to see how I actually implemented that. So does it work? What we see is that the DEformer generates realistic samples while still being entirely order agnostic. So these are test images on the left and some generated images on the right, and they look not bad. We also see that the DEformer can effortlessly fill in missing values in a variety of patterns like we talked about before. And so the left-hand side here is the ground truth, and then we pop out some pixels in various patterns, and you can see that the model seems to do a good job of filling those in regardless of what the pattern is. Additionally, the DEformer is actually competitive with both fixed order and non-autoregressive models. So you can see how the DEformer compares to some other models on the MNIST data set and the power data set here on the right. And you can see that's in the ballpark of both. One thing I want to know, so TRADE is a fixed order transformer distribution estimating algorithm from Amazon. One thing I want to point out is that I did not do a ton. I did actually very little hyperparameter tuning for my model. And so I feel reasonably confident that with some careful hyperparameter search, I could match or potentially exceed the performance of these other models. And so in that case, we'd be getting both state-of-the-art distribution estimating performance while also retaining these order agnostic properties, or basically just coming along for free. Also, we found that the DEformer can easily distinguish between in-sample or in-distribution and out-of-distribution samples. And so as our out-of-distribution data set, we use the not MNIST data set, and you can see some samples of what that looks like here. And so basically for each of the MNIST test set images, we assigned it a negative log likelihood, and then we did the same for the not MNIST images. And what you can see here is that the distribution of negative log likelihoods for the not MNIST data set is much, much, much higher. So like you'll notice that the scale here is like in the thousands, and over here the max is 160. So basically the model has a really easy time distinguishing whether or not something is in distribution or out of distribution. So to summarize, the DEformer uses Levent interleaved input design to perform order agnostic autoregressive distribution estimation. The deformer can generate realistic samples and effortlessly fill in missing values in a variety of patterns. And the deformer is competitive with fixed order and non-autoregressive algorithms and can effectively recognize out of distribution samples. So I think there's a lot of potentially interesting ways to extend the Order-Agnostic and related architectures. One question I think would be cool to explore is what happens if you train a single Order-Agnostic model on multiple sports, for example, soccer and basketball. So I think for me personally, intuitively, what it feels like is I feel like there are some aspects of sports that translate between sports, for example, like athleticism and agility and things like that. And so would a model that was trained on multiple sports be able to transfer some of that like athleticism knowledge between the two and have better performance on each compared to a model trained on each sport individually? I also think there's some potentially interesting uses for long-term outcome forecasts. And so as an example, you could, as sort of one particular example, we might be interested in, given a frame, we want to predict whether or not a shot will be made in the next 4 seconds. So 2 alternative strategies. The first one would be build a classifier and just classify each frame, whether or not there was a shot made in the next 4 seconds. But the issue there is that you have class imbalance, and you also have the issue that the samples are not IAD. So like, you know, a 2 frames that are next to each other are not independent. They're obviously correlated. So an alternative strategy might be to just simulate the game using Order-Agnostic and then count how many times the ball ends up in the basket. And so in this case, we're training the model on sort of the physics of the system, which has a much denser learning signal and doesn't have these IID issues. And so it'd be interesting to see if that type of sort of physical model, if you will, would perform better for long-term, for forecasting long-term outcomes. Lastly, I think this Order-Agnostic architecture is like pretty flexible. It doesn't have to necessarily be applied to multi-agent spatiotemporal data, actually, as I just demonstrated with the deformer. And so it'd be interesting to see how it works on other types of data sets, for example, social media data sets where we have users interacting through time. Okay, and with that, I'm happy to take any questions. Let me have people muted, so let me unmute. Want to. I can hear through this. I'm not actually sure.
Michael,
Yeah.
This is Levent, Yilmaz. Very sound, very interesting work. I might be biased though, because I like basketball. I'm a basketball fan. And I used to play as a point guard, as I told you earlier.
Yeah.
So I don't have any questions because I think looking at the write-up of your dissertation, I realized you addressed all of my comments. But I'm just curious, can you actually look at the problem at different levels of resolution and abstraction by looking at how the teams are oriented? What is the trajectory of a team overall? Because a basketball game is like a harmony. The team players, play together in harmony and they move together. So I wonder if you can predict a group of players, how they move together. And can you maybe overlay your approach with some graph theory to be able to accommodate that kind of information?
Yeah, so I think Order-Agnostic is like kind of doing that. And so, yeah, I mean, there's like so many different directions I could take this question. So yeah, like you can interpret actually the attention mask as encoding a graph. And so I actually talk about that in Order-Agnostic, how that particular mask is equivalent to assuming a fully connected graph at each time step. And so, yeah, I think the Order-Agnostic plus is sort of, I think, getting at what you're talking about, because every player is connected to every other player, and so they can see what everyone else is doing, which induces that statistical dependency. And so, yeah, like even though I only showed for that Order-Agnostic example where one player was going, that was just sort of for ease of understanding. I can simulate entire teams through time and you can see that they have coordinated behavior. I probably should have thrown in a GIF of showing that, but you can see that the Balderbeck plus model.
Sounds good. That's a good answer. That's a good answer. Just one more, comment. I would be curious if I were an assistant coach or a team manager or a coach of a team, I would like to know, interpretable, explainable rules that tells me, if the game is in a particular state, then, I would like to play with a particular pattern, right? So can you generalize and come up with some symbolic knowledge that can actually provide some general purpose rules for not only players but the coach and team managers?
Yeah, I think you could sort of throw some constraints perhaps on the behavior of things, or like I've also thought about like, so like you could force the model to only be able to predict like within like a physical limitation or something like that. So like the physics of I kind of implicitly encoded some of these physical limits by only letting my trajectory bends have limits. So I only allowed players to move up to 5 feet in either direction within a time step. But yeah, I think you could do maybe certain encode sort of other inductive biases like that into the architecture and see how that would work. I think it's still, I think is a challenging, even if you like sort of force these inductive biases in, I think it's still hard to get at like whether or not you can trust your counterfactual things. And so I think eventually you just have to like build up enough of a training data set and have a strong enough test set that's variable enough in the ways you want. So Balderbeck is actually an extension of, or sort of a spiritual successor to a project I worked on before I started Auburn called Batter Pitcher Debeck, where I was predicting outcomes of at-bats in baseball. And in that case, my test set was completely unseen. So I trained on 3 seasons of data, and then my test set was unseen batter pitcher matchups from a completely new season. And the performance on that data set was, it worked well. And so I think for me, the most convincing way of showing that your model is robust is by finding that kind of test set that really gets at whether or not the model's understanding, is actually trying to model the inherent qualities of the system, or whether or not it's just like picking up on correlations that when you try to actually use it to make decisions will not behave in the way that you expect.
Okay, sounds good. Thank you.
Thank you.
That's all I have. Thank you.
Hey, Michael.
Oh, I got one question in the room, then I'll get you, Jan.
Oh, yeah, sure. Yeah.
Thank you.
Yeah, sorry. So I just wanted to extend the question a little bit. In the game theory perspective, we have this cooperative and competitive behavior between the agents.
Yeah.
And so like, did you try to think on like how you can evolve or find out the strategic behavior of the individual agents? Because, sometimes agent could be selfish, and, the behavior could be like, instead of cooperative decision, which can shoot the ball, they can evolve the behavior like, like it will be selfish and then it won't be like basket or something like that.
Right.
So you talked about like cooperative relationship in your statistical model or something. Did you think on like, how you can evolve the individual agent's behavior?
Yeah. So I think this also kind of is related to the other question about like counterfactuals and stuff too, because like say you we're trying to use Balderbeck to like optimize a play that would cause a certain outcome, and say it tells the point guard always go to the right when it's facing this defender. And so like if you always go to the right, like the defender is going to learn that and he's going to defend against you, right? And so like that strategy actually isn't even valid anymore. And so I think you need to, there's like one thing I've been thinking about, this is like sort of like a really ambitious project, but like would be to set up the rules of basketball and then have 2 Balderbecks that are competing against each other and see what types of rules come out of the system in that case. And so like you can maybe train a Balderbeck model on the NBA data set, which sort of gives you the physics, perhaps, if you will, of each player and like their skills. And then you use those particular physics and skills in this like game theory setup where you have these 2 competing models and see where it goes.
Oh, okay.
Yeah. Yeah, Jan.
All right, thanks for another great presentation, Michael. I have a few questions for you as well. So the first thing I was wondering, in sports analytics, it's often relatively hard to obtain data. So do you have any thoughts how much data would be required to train Board-to-Vec and Board-to-Vec++ models that are sufficiently accurate to be used in practice?
Yeah, so I mean, I feel like the results of this Board-to-Vec were like pretty encouraging. That was only a half season of data. And so, yeah, I think one of the real selling points of Board-to-Vec and Board-to-Vec++ is that it doesn't need labels. And so all you need is basically video that's been translated into coordinate data. And because you're just using the trajectories as the signal. And so I don't like, and for basketball, it seems like half a season was enough, but there's obviously issues with like sort of overfitting to the season in that case. So more data would be helpful. But I think, yeah, one of the real selling points is the fact that you just basically need the video translated to the coordinates.
Yeah, makes sense. And well, you develop Board-to-Vec++ to address some of the limitations of the original Board-to-Vec. So if you or someone else were to continue to develop the framework, what would be the most important limitation of Board-to-Vec++ to work on?
I think if I was like really trying to get like the completely optimal model, I want to start really integrating more contextual information. So about like the amount of time that's left in the quarter, what the score difference is. Like I talk about all these things in the paper. And so like the age of players, their injury history, just all these different factors that can affect the game dynamics, and then really extend the data set to multiple seasons so like the idea here is that with incorporating all these different potential like causal variables, and then with enough historical data to introduce a lot of variation within these inputs, you actually can get to a point where you can start trusting the counterfactuals and be using it to do that type of, or use it in that type of decision making.
Yeah, makes sense. So, well, I still have two more questions, if that's okay. So the next question is, like, for someone working inside an NBA franchise, what would be the main application of Board-to-Vec? So if I were, for instance, the general manager or the head coach, how could I use your models in practice to improve the performance of my team?
Yes, I think the thing that's like kind of interesting to me would be to use it for like evaluating trades and things like that. So I think you could potentially sort of find underrated players, for example, who are like, the model thinks have similar skills to like a really highly paid player, but maybe because of their particular situation, they're not being utilized in a way that's advantageous. So I think that's one application. I think it would also be interesting to apply Board-to-Vec to like college data, and like try and jointly model that potentially with the NBA, and so like project, you know, draft picks and things like that, how they'll perform.
Yeah, cool. And finally, yeah, you know that I'm a big soccer fan, and that I've recently joined a soccer club as well. So what would be the main challenges if I were to apply Board-to-Vec to soccer data? So would these approaches work out of the box? Would I need to make any changes to these approaches? Or would I simply need more computational resources or something else?
My guess it would honestly work out of the box. That would be my guess. So, I mean, the fact that this architecture worked on image data and tabular data too, I mean, it's basically still exactly Board-to-Vec. I don't see any reason why it wouldn't work on soccer data, especially since it's only like twice as many players essentially. Yeah, I think it would, my guess would be it would work out of the box.
All right, thanks a lot.
Thank you.
Hey, Michael, I just have a small comment about the ODA, the one that you presented at the very end. So you won't, at least in the presentation, you only seem to be testing it on the MNIST data and the power data.
Yeah.
I'm not much aware of the power data since it's more of a tabular data. But I have worked with MNIST. So have you tried it on ImageNet data? Because that data is much more complex and more towards the real life. So have you tried it on the ImageNet? Why I'm asking it is, or the other way to put this question is, how can I use this model for, say, image imprinting task? Because this is one of the challenging aspects that people face in computer vision. So there'll be very interesting application of this ODA model.
Yeah, so I think the issue with, it wouldn't work with ImageNet because of the size of the data.
Mhm.
So transformers have a quadratic complexity with the size of the input because of the attention mask or the attention mechanism. And so, MNIS is 28 by 28. And so our image net is, like 224 by 224 by 3. And so squaring that, it's not even, I can't even do CFAR 10 out of the box on. And so I think theoretically, I think this type of, that applies to any, or if you want to do order agnostic stuff on ImageNet, like you're going to be running into like complexity issues because like the way generative models work with images right now is they exploit convolutions, right? And so they're able to handle these highly dimensional inputs. And so I think to be able to apply these types of architectures to something like ImageNet, you would need to come up with like sort of really clever attention mechanisms. Actually, on that note, you'll recall, let me reshare my screen. I actually think it's kind of interesting how early in the image on the right, you can tell what the digit is. And so like after like about 20%, probably you'll all be able to tell that it's 7. And so I think one thing I've been like thinking about with regards to this result is that, maybe you don't need to attend to everything. Like you could randomly attend to earlier inputs in the sequence, and that might be enough to like sort of model the distribution later. But I think the sort of application of this right now, I would imagine, is like these Internet of Things things where you have like a tabular data set effectively, and you're trying to, detect anomalous behavior and things like that.
Or maybe you could try out some of the latest advancements in transformers where they try to reduce this n square complexity to maybe n log n, or they are going for
Right. Yeah.
complexity, but
Yeah, I talked about some like sparse transformers and stuff at the end of the DEformer paper about how that might be an avenue too. But yeah, I think there's like, I think it would be interesting for someone to figure out, but I think you'd have to have a lot of computational resources to be able to like experiment and stuff. Does anyone on the call have a question? Got one. Yeah, I think someone in the call was going to ask something there too.
I have a question about just a kind of a different situation, which maybe this border to Vic. So you've got, let's say you've got ocean current information. Like since the 70s, people have sent out these buoys and they've measured the trajectories of these. You can measure the trajectories and the velocity of these buoys. And and at the same time, there's kind of this overarching physical understanding of macro scale models of how the ocean currents go. And that would be kind of a constraint on your model. And so I was curious whether it's possible to, I think you kind of alluded to the need to kind of impose perhaps some context to your, let's say, to your game or something like that. Whether would it all be possible to, I don't know, use dynamics, some sort of partial differential equation to kind of impose some sort of context, although it might, the dynamics might just be kind of large scale. Have you thought about that? Or I'm just throwing this out as a PDE person.
Yeah, I haven't thought about that. I know people are doing like stuff with neural networks and differential equations. Like that's like been pretty hot the past few years. Like I think there's a paper called neural differential equations or something like that. But yeah, I'm not sure how I would approach something like that. So yeah,
I would just to predict, let's say for instance, predicting the path of a given buoy in a region or a group of buoys. And so think of them as players. Yeah. And so you can kind of, you can use border to vec plus because the movement is correlated and it's there's this underlying hidden variable that's kind of dictated maybe locally or kind of on a larger scale by dynamics. And so, would it in principle be possible to predict the trajectory for the next day or two of a buoy for whatever use that might be. But you know,
Yeah, I don't see any reason why like you couldn't at least model that just with Levent++. What I'm less sure about is like how you would like incorporate some of these this like sort of background scientific knowledge about like with these differential equation models and things like that.
right.
That would yeah take some more thinking, I think, on how exactly like you'd be able to plug that in. But yeah, I'm wondering if like there's a way to use as an additional input or something, like whatever these constraints are as an additional input to the model or something, or
Right.
yeah, I don't know, to somehow constrain, like, so I mean, like with Balderbeck again, like what I was able to at least constrain the players physically. And so no player can go further than 5 feet in either direction in a particular time step.
Right.
So like maybe you'd be able to inject some of those type of constraints like through the loss function or something along those lines.
Yeah. Thanks.
You.
Hi, Michael. I really like most idea you have presented. Well, I'm curious, one question. You have mentioned that Belfour VAG is a multi-agent system. I acknowledge that multi-agent system always will be far more complicated than single agent. So my question is, were you actually setting up all players with an individual learning model, or you just predict one player on one AI model and let all the other players what it is?
Yeah, so this model is jointly processing all of the players simultaneously. Yeah, and so yeah, it's not like I had a single model for each player and then combine them at the end. It's actually jointly processing them all at the same time.
Okay. Thank you.
Thanks. Yeah.
So thanks, Michael. That was great presentation.
Hey.
Just to be certain about one thing, so the attention mask you had is, if I get it right, it's trained over periods of 4 seconds, more or less.
Yeah, that was the
Okay.
data set.
Okay. I'm assuming that going beyond that wouldn't have much sense, right?
I mean, yeah, so like basically how long you do determines how much like long-term information you can keep into the model. So I mean, you could theoretically, I mean, given enough computational resources, you could train on like the entire sequence of the game, for example.
Yeah.
And that would probably be useful in some regard because like the players are less tired at the beginning, the model might be able to learn that, but that'd be an incredibly large
Yeah,
input.
exactly.
Yeah, so in terms of practicality, it might not be feasible.
Yeah, no, because I was thinking, given if you wanted to extend that, I don't know if even if it's practical or useful, but in any case, the attention mask could have the lower diagonal part becoming empty after a certain time.
Yep,
Right.
yep.
So have a short memory kind of Markov process kind of procedure.
Yeah, for sure. And so like that's some of the sparse, I think I mentioned the sparse transformer stuff when answering Alma's question. And so yeah, like that's an active area of research with like at like Google and Facebook. They're like trying to figure out these long-term transformer problems. And so they're introducing some of these sparse attention masks like we're talking about. The issue with sparsifying mask, and so like yeah, the diagonal actually would be cool because you can still I can send you a paper actually on this that you might find interesting, is that with the diagonal way, you are still able to exploit the GPU. But if you like try to sort of like what I mentioned earlier with like using like a random sort of attention mask where you only attend to certain things in the background, you can't use the GPU, like that's basically random access, which GPUs aren't good at. And so like you can't, that slows down your model training considerably. So you might have to be kind of clever about how you incorporate that kind of thing. But yeah, like these sparse transformers might be one way to do that.
Then I just had another one regarding the first chapter. So you studied how these networks behave, the different poses and all that. I'm not sure if I maybe have missed it, but if there was a take-home message on exactly what kind of poses or transformations were facilitating them, and based on that, whether you understood or had an idea of how this could be addressed to limit the error.
Yeah, so and I mean a large percent of the poses were misclassified. I mean, and there was always like, so like each object you can imagine has a canonical pose, which is like the pose we're used to seeing the object in. And that's like what the 3D object was initially oriented in. But even, and so like there are these biases in the data set, so you could try to extend the data set to try and fix those, but you're still like the possibilities of poses are like, it's infinite, right? And so what I think you need to get at to really be able to, not worry about different types of poses causing an issue is like to really have an understanding. A model needs to like sort of have a physical, intuitive understanding of how the world works. And so like, I think like babies are the correct way to do that, right? Where like, so yeah, you guys saw the picture of my daughter, like all she does is do experiments. And so like babies are constantly picking up toys and like manipulating them. And like this one behavior Roz was doing, my daughter was doing for a little while was everything she picked up, she would touch to the back of her head. And so she was just seeing what happens when she puts this thing on the back of the head. So like through all that experimentation, you're like learning these incredibly powerful physical common sense models. And so I think that kind of like, if we could train, like you can imagine sending out a robot, the robot can take an action and then see how its input, it's predicting how the input changes. So like it sees an object and says, I rotate it like this, I try and predict what the object will look like when I rotate it. So if you had a model like that, I think it would be able to, handle, like obviously humans can handle any type of pose. And so I think that's sort of my dream of how that thing should go. And it seems like you have to get at some sense, be able to get down to these sort of causal physical models to really have a common sense understanding for these types of things.
So I guess that in the end, what it comes down to would be just have a labeled object, rotate it many times, have it map.
Yeah, I don't even
be increasing the set of outputs and matchings at that point, I guess.
Yeah, so you don't even, I don't think you even need labels, right? So you could just, if you just imagine you have, so you have the image come in and you just predict the image that happens when you rotate. And so you don't even have to know the label. I can just predict how this thing's going to go.
Yeah.
And so like, I'm learning this really rich representation of the world just by like doing experiments constantly, so.
Michael, I have just get to know kind of information for the methodologies. What is the time of the training sequence in the Baller 2 WEG? You picked the training sequence. So what is the time of the training sequence from the whole set?
It's 4 seconds is each training sample.
So 4 seconds for each training set. And so you talked about the transformer. And so I have really shallow knowledge on the transformer, but so you talked about you look at the information in the past. So all the information. So you are looking at the information of what happened everywhere all the past, or like what is that time sequence? Because if that we can easily run into the complexity issue, and so like how long you are looking in the past.
Yeah, so it only, what I mean by that is later in the sequence, it can look in the past at what happened early in the sequence. So if I'm processing the 3.5 second time step,
so it will look at
0 to 3.5.
0 to 3.5. And so connecting that, I have just another question. So you mentioned you were looking ball trajectory feature all the way in the Baller 2 WEG. And so, in game theory, we also have like complete information and partial information of all the agents and things like that.
Yeah.
Like you also have any kind of information that you in the future gonna look for, like if I will give just partial information, how my model gonna perform? Because right now you are giving information for the ball trajectory, maybe from all the players. So how all the way ball is passed from one player to another player. But let's say if you are just giving the information of just 2 players and then you don't know that ball, what is the trajectory of the third player's ball information, and then how models gonna perform or something like that. So what I mean by partial information, and then how model reacts to that partial information.
So Order-Agnostic could actually handle that case because it's order-agnostic. And so I can condition. So if I only have 2 players, I can condition on those 2 players and then predict every other player's trajectory and go from there. So yeah.
Okay, yeah. So just get to know. Okay, so Baller 2 WEG plus have that kind of agnostic behavior. So like partial information can also predict it.
Yep. Absolutely. Yep.
Thank you. Just a continuation of that question. did you face these kind of partial information cases when you were generating the data? Because one could imagine while creating the data from the videos, in some frames, only certain players will be visible. So did you face such situations while creating the data, or how do you make sure that all the players are available in that 4-second time frame period?
So this is, I was given the coordinates of all the players in the court. And so there's no missing data in this case.
Okay.
Yeah.
You said you created the data set from the half season videos, right?
And I use a half season of data. Yeah.
Okay, so it was already in the coordinate format. So to
Yeah.
say.
Yeah.
Yeah, but yeah, it can be a challenge because as such, we would only have the videos of the game coming in and how to, yeah, it's an interesting question, how to handle the
Right.
partial information.
Yeah. Yeah. For sure. Yeah.
Thank you for your great presentation. And I'm interested in video games. So is it possible to use your Order-to-Vector architecture to improve the AI bot for basketball game or even soccer game?
Yeah, I've actually thought about that a little bit too. I think that would be cool to try. Just to throw, because you're like literally modeling the physics of the game. So it'd be interesting to see what happens if you use it for the AI in the video game. I do think video game designers often intentionally change some of the physics though to make it more fun. And so it might not necessarily translate well, but it would be maybe a starting point that they could then really do it rather than start from scratch.
Another question is, if I a coach of the basketball team, so and I want to apply some strategies for my team and see how my team behave against the other team, is it possible to use your model for this case?
Yes, I think with either Order-Vec or Order-Vec, maybe you prefer to use Order-Vec++, but yeah, so you could basically just have the offense, and then so there's two ways you could do this, I guess. You could have the offense and dictate, so you could like draw a play where the players are going to go, so that would be their trajectory at each time step, and then you could let Order-Vec++ simulate how the defense would respond at each time step. Alternatively, a way to do that, something you could do would be to have an encoder decoder type of setup where you have you put in the entire offensive sequence, and then you try and predict what the defensive sequence would look like given that offensive sequence. And so that would be another way to try and see how the defenses would respond.
Thank you.
I think just a comment. I think I see a lot of applications here. This is maybe not just for the sports, but maybe for the robots. They can apply Order-to-Vec or Order-to-Vec++ for a particular goal to achieve and stuff like that, where they come across the defensive mechanism in the real world, and so they can be like as an agent bypass all those things and then try to.
Yeah, I just saw a manuscript pop up on Google Scholar that was doing like traffic predictions, like a pretty common multi-agent problem, and they were using the graph recurrent neural network, and I was like, I wonder what happened if I just did my guess would work better, because again, like you can just scale up the transform. They blow recurrent neural networks out of the water almost every task. So I guess it would be that would work better. But yeah, I think any sort of system where you have multiple inputs moving around or interacting in complex ways would be an interesting way to.
It would be really neat if you can extend the methodology where system can take the features no matter what kind of application it is. So it can just take the generalized features and then just, you give the features, you give the goal, Order-to-Vec finds the way of predicting the trajectory and then try to reach to the.
Yeah, I feel like it would probably be hard. So I guess, yeah, I don't think you could necessarily freeze the model and then like try and learn the features, because I think the physics are so different between these different systems. But it'd be interesting. So for example, like that basketball soccer example I was talking about, where you train a single model on basketball and soccer, you could envision on the sport. So like include whether or not it's basketball or soccer as an input or something like that. Now the model's learning the physics of both of these systems essentially, but it's allowing the things that transfer between the two sports. You can learn those properties.
The athleticism and all those.
All right, any more questions from the audience? From the Zoom audience?
I don't think we have more on Zoom.
Okay, so thanks, Michael, again for a great talk, and thanks for your very interesting questions and discussions. I think the next phase is we will invite everyone out of the room. You could wait outside, or the committee will discuss the